Hello. My name is Ryan Easterbrook. I am a technical lead at EventMobi. I focus primarily on our backend architecture there, written in Python. If you've used the Event app for this conference, then you've seen some of our technology already. So we are a platform of technology for event organizers to make their events better using technology. So the Event app is our flagship product used for conferences like this one to help provide you as attendees with a list of speakers, of sessions, being able to create your own agenda. So in 2010, this is roughly the products we had, products and features, 2013, 2015. So it grows pretty rapidly. And some of the challenges we're facing is having thousands of clients with customized needs. Event organizers want to have a lot of control over their events, including branding, sponsorship, white labeling. We have multiple products that all need to be integrated together, requiring the same data. But we have many different teams working on them. So this brings up questions of ownership and communication. We have major features in different distinct categories which require different skill sets to work on. Things like document management, real-time communication, ticket payment into client accounts, and language localization. And probably like many of you, working kind of startup type environments, we require really high velocity to get business value out quickly to our customers and remain competitive. So the reason I'm telling you about our challenges is to provide context. You might not have the same challenges as we do. Maybe you do, maybe you don't. But they always differ. So given these challenges, which of these are the right, what's the right answer here, right? So what I want to talk about today is that we spend a lot of time focusing on questions like this, one or the other, saying this solution is better, let's always do it this way. What I think we need to spend more time focusing on is the underlying principles beneath these about how do we build systems that can be decoupled and scalable and really suit those to our own challenges, our own needs, and build from the bottom up. And maybe it will resemble one of these, maybe not, as opposed to kind of trying to pick one of these and build from the top down and try and shoehorn our applications into that. So to discuss architecture, let's define it. So I like this definition from Martin Fowler, that things that are hard to change. I think there is a certain intuitive sense to this. If nothing was hard to change in software, then we wouldn't need architecture. As business needs changed, we'd just change the software to meet the business need, and there'd be no mess about it. But over time, things do become difficult to change, and architecture really then is a solution to try and mitigate that from happening, to try and keep things easy to change, or try and create certain patterns which over time allow that change to happen more easily. So if we're talking about things that are hard to change, kind of the principal offender here is coupling. So coupling is the degree of interdependence between software modules. And by itself, coupling isn't a bad thing. If none of your modules are coupled together, then you effectively don't have a cohesive system. Any modules talking to each other will have some coupling. That's why we talk about in terms of low coupling and high coupling. So you want to try and keep things decoupled, loosely coupled, as opposed to highly coupled, so that each one can be changed in isolation from the others. When you get high coupling between components, it ends up looking something like this ball of mud or spaghetti code, which many of us are probably familiar with. Technical debt. I'm defining this here as the accumulation of non-ideal code. And often things that we think are temporary aren't. So the reason I define it this way is because there's a lot of different types of technical debt. So for example, maybe you have 1,000 files that aren't following a consistent style guide, and you want to move it over to being that style guide. That would take a lot of effort, and so that is a high amount of technical debt. But in itself is not a coupling concern, for example. It's not like a scaling concern. So when we really care about these things is when technical debt due to coupling makes change impossible. This is when we need architecture to address this problem. So if you're working on a small project, a startup, you shouldn't spend too much time, I think, focused on this at the onset. You want to address it before it gets to the point where change is impossible, but you don't want to focus on that necessarily initially. So this is more about when you have a lot of stuff and you need it all to kind of keep moving, keep evolving, to continue to meet new and changing business demands. So some strategies to mitigate coupling. Boundaries, single responsibility principle, strong interfaces, and encapsulation. So these are the ones I'm going to talk about today. They kind of are all interweaved and all work off each other. Boundaries. Boundaries is basically taking a larger thing and dividing it up into smaller pieces. So represented in the diagram, we see we take our larger ball of mud from before, we've broken it into smaller boundaries, and it can still be messy and complicated inside of those boundaries, but it's smaller, it's easier to reason about, and the communication between those boundaries can be more clear. So in this case, if I want to work on this part, I can focus just on that part and on its communication with the other boundaries without having to know the internals of all of them. I'm also going to probably be using the term components interchangeably here with boundaries. So here's a really simple, kind of overly simplified example of some code that takes in sports sites, is designed to then go scrape the web to pull scores, and then save those scores in a database and return that data. The scraping here is obviously radically simplified, so is the rest of the logic. So I would say this is not very well designed code because it is mixing together very different concerns. In the same function, it is doing a web request out, having to handle whichever logic is needed around the web scraping, which would likely be quite difficult and much longer than is represented here, as well as whatever is needed to persist that to the database, and then the processing kind of manipulation of data in between those two things. So we'll use this as a way to kind of demonstrate boundaries. A way we could split this up is more like this. And I've omitted the implementation because it's not that significant here, but you can tell kind of just from the functions what part is doing what now. If we want to understand just at a high level what our update scores function does, we can see it gets scores and it saves scores and then it returns scores. Very simple. If you need to dive into the details of a given function, you can do that and see how it's implemented. If you need to modify how it saves to the database, you can do that without ever having to worry about the web scraping code, for example. So here we've created some boundaries. Each one of our boundaries, in this case a function, has a very clear interface. And each function is responsible for a single thing, following single responsibility principle. The details of the implementation, say writing to the database, can be complicated, but it's encapsulated into the function. behind the interface. Same example, this is just kind of a diagram representation. We could kind of see here how one component could be removed, swapped out for another without having to change the whole thing. Whereas on the left, it's kind of just a black box. Again, overly simplified example, but hopefully it demonstrates the point, which is somewhat hard to do with code. That small amount of code for a presentation. So, how to decompose into boundaries? Essentially, if this is a good thing, how do we take our code and turn it into boundaries? How do we know what is inside? In this case, I'd really recommend trying to map your components as closely as possible to your business needs. Try and keep a low level of abstraction between the two, and use ubiquitous language to make sure that the representation in your code is the same as the business. Right down to the same words that your clients use, that your business experts use, and that is in your code. Try and keep it as much as possible one-to-one. The advantage here is that it makes it much easier to hold a conversation with a business expert. A way of validating this is actually sitting down, and I recommend doing this, with business expert, showing them a high-level representation of your boundaries of your entities, and seeing if they understand it, and they should. That's how you know that what you're building is at the same level of abstraction as the business need you're trying to deliver on. And the closer it is to the real need, the less likely you are to have to change it, or the more resilient it will be to changing business needs because it will better represent them. You can still have more abstract components beneath these, but the more surface level ones should be pretty clear. Other than that, it's hard to give general advice because this is very dependent on your own needs, on your own business, and it's a hard thing to get right. Generally, I think it's almost impossible to get right initially. We shouldn't expect to or presume that at the beginning of a project we will get the boundaries right. You need to gain an understanding of your business, work through it, and iterate. This is an example of how we do this at EventMobi. A simplified example, but these are real domains. Essentially, one domain roughly maps to a team. A team owns one or more domains. Inside the domains, we see components or services, and we can tell the relationship between them. So in this case, we've separated out organizations from events from registration. And within these, we further subdivide it. So we can see here that organizations have events. In this case, events know about organizations, but organizations don't know about events, which is the way the arrows point. We can see events have sessions, like this one, speakers like myself, and attendees like yourself. And we can see that in registration, we have a registration concept, we have registrants, and we have tickets. So we can see that this maps the way we've written our software, that we divide our boundaries, maps very close to the real world domain of an event like this one right here. You can actually go to our code, find a speaker's event, and see the representation very easily. Boundary size. So how big should these things actually be is another kind of common question. We saw earlier that a function could be a boundary, a class can be a boundary, a Python module could be a boundary, a separate service or application could be a boundary. So, and generally you'll have all of these together. The same kind of pattern exists inside your code as kind of at the system level. The general rule of thumb here is not 10 lines of code or 1,000 lines of code. It's whatever it needs to be to follow single responsibility principle. Keep what's in your component cohesive. Keep it kind of all on the same topic. Whatever needs to be there should be. But keep it doing a single thing. And if it's doing multiple things, break that out into multiple components. Boundary protection. So this is essentially making sure that your boundaries are enforced. So you do this by using strong, standardized interfaces. What this does means you can encapsulate the complicated internals of your implementation behind the interface, which allows you to swap out any part of those complicated internals without breaking any other part of your system. And this is really a key part to keeping your system decoupled. It allows you to make change whenever you need to and not be too tied to your technologies. It allows for complex composition of components. So if you have standard interfaces, you can understand what a given component does very easily without diving into the internals. And if your interfaces are standardized, then you can write automation around this and combine different components together to actually get the functionality you need. And it prevents accepting or leaking bad data. Essentially, you know exactly what is coming in and what is going out because it meets the interface. So here's an example of how we do this at EventMobi on our backend Python code. We have a kind of strictly defined contract where we specify types, somewhat similar to, say, a SQL Alchemy model, for example. We specify the types and various other validation rules. As data comes into this, it ensures that that data is correct, that it is the right type. It'll do things like set a default if that's not there, and really contains kind of that generic validation code that needs to be somewhere into this standardized interface that can be reused. But the interface is also implementation agnostic. So behind this could be SQL Alchemy or NoSQL or Redis or S3. It doesn't matter, and you could swap it out. And then we have, in this case, a service, but this would be our component. And we're just saying it uses this contract, and we can take actions then based on that contract. So when we kind of combine all that together, we get something that kind of looks like this. In our case, it's running inside a single process, a single Flask process, although the Flask has been kind of pushed only to the top layer. And then beneath that, we have a series of components. Each one has a contract, and the components can talk to each other. Different components can own their own data sources. Components don't share data sources. They'll need to access the data through other components, keeping the data encapsulated inside that component. And meaning you have to access it through that strong interface. And we can see here that through a similar standardized interface, the data source can be whatever we need it to be and can be swapped out if needed. So back to kind of those original questions. These are just kind of my own views, I guess, on it. So my view is build a decoupled monolith first. Use that to iterate, find your boundaries, change them, make sure they're correct. This is, again, difficult to do right the first time, but it's really, really important that you get it right. After a while, your business will probably stabilize to a degree. And then if you need the kind of performance or scalability, whether that's scaling your team or scaling your traffic, then you can start to break it down into separate processes and microservices if needed, which is much easier to do if you already have well-decoupled components. RESTful versus event-driven. RESTful is a great interface for kind of standardized talking out to the world right now. So for any kind of third-party integrations, as well as for your own client integrations, it's still a great way to go. Something like event-driven probably makes sense if you need to start solving more complicated transactional problems in the backend. But again, something you should probably evolve to if needed and not taking on the additional complexity to begin with. SQL versus NoSQL. If you have strong interfaces that encapsulate your data storage implementation, it doesn't particularly matter. You can use whatever is best suited for the particular piece of data that you're working with at that time. So to sum up, decompose your system into simple components that do one thing and do it well, with clear boundaries, protected by strong interfaces, that communicate with simple and consistent rules. Some references, Domain-Driven Development by Eric Evans. This is a really great book for diving into boundaries, domains, and helping you understand how to break these things out to meet your business needs. And Solid Design Principles is just a very fundamental, good principles of object-oriented programming, which apply regardless of whether it applies at the systematic level as well as at the class level. Thank you.
Well, the floor is now open up for questions. Ryan, do us one favor, because there's only one mic, repeat the question when you hear it. Thanks a lot.
So you said you should like make sure to maintain the boundaries, right? If you start with a monolith, your repository has all these tiny apps, and you have like the organization team and the registration team, and like you have all sorts of different teams. How do you ensure on your like in your tool set or something? How do you ensure you're not breaking these boundaries?
Right. So the question is, how do you maintain boundaries within a monolith, effectively, right? When you potentially have multiple teams, multiple developers all working on it. Essentially, it takes more discipline than if you have a separated process. The advantage is that a monolith is just a lot easier to deal with at first, especially around anything to do with infrastructure, deployment, and communication. So I think the ultimate, really you have to make doing it the right way the path of least resistance. It has to be easier to do it the right way than to do it the wrong way. Otherwise, people will do it the wrong way and you'll have to be on their case. Things like good code reviews help a lot as well. Make sure that someone who kind of is aware of the architecture is doing code review initially, and then train other people up on it and get those ideas to spread. But really, it kind of comes down to discipline.
Kind of aside from your main point, that contract class that you're inheriting from, is that something of your own design?
Yeah. It's essentially it's using, oh, sorry. The contract class is that our own design. Yes, it is. It's relatively, it's probably like 300-400 lines of code. It kind of evolved over time as we created a RESTful framework that sat on top of Flask to kind of making RESTful endpoints really easy. Kind of came out of that as the validation layer for the front end that was unopinionated about what the implementation behind it would be. And essentially uses a meta class to pull out the attributes and generate properties that can validate data going in and out to ensure that it's not being violated.
So the API for that looks a lot like traits, another Python package. You invented your own because it evolved naturally, or this does something different from traits?
So he's asking that it looks quite similar to traits. Essentially, traits isn't something I'm aware of. It did kind of evolve on its own. I think one of the advantages of doing it this way, I mean, I am a fan of reuse, but also within reason. There is some advantages of rolling your own, depending on the complexity of what you're rolling and how central it is to what you're using. The advantage here is that internally we know the code inside and out and can match it to exactly what we need for our business case. I think the more generalized of a solution that you use, it's great in that there's resources out there and it's stable, but the more general the solution, the less tailored it will be to the actual problem that you're trying to solve directly.
How did you know when you needed to start splitting things out into a microservice?
How did we know when we needed to start splitting things out into microservices? So we had or have kind of a legacy PHP monolith. So this is kind of a second system that's been able to kind of be developed on the side. And then we've rolled all new feature dev into it. And now we're kind of rolling all our old features into it as well. So we did take the approach of rapidly building out the simplest thing we could first to get features out the door and get clients. And I do recommend doing that. Like I mentioned at the beginning of the talk, don't necessarily worry about focusing highly on decoupled work until you need to, because it does add a lot of complexity and in some ways slows you down until you need it. So we build it on the side. Like I mentioned, it's all in a single process right now, which has really kept the complexity down because we haven't had to take on any of the distributed system concerns yet. Yeah.
In your example with events knowing about organization, how would you deal the cascade delete? If you delete an organization, how would you cascade delete the events which are related to an organization, knowing that it is different, it might be different at that store?
So essentially, how do we cascade deletes if an organization is deleted? How do we know to delete the events? Essentially, right now, it'll just be kind of a synchronous call at the end of the organization call. The tables are decoupled in that two components don't talk to the same table, but they are in the same database. Our plan to move forward with that is to move to a pub subsystem. So at the kind of service interface layer, when an organization is deleted, it will publish an event, and then the event service can listen, or some other thing can listen to that, and go and delete any child events if needed.
We have time for probably one more quick question.
Okay.
So you said that you guys started off with monolith and then you switched to a more decoupled system by starting over, right? Or was that? I assume you meant starting over. When you do that, don't you end up losing a lot of the work that you've already done? And in that case, wouldn't it be better to just start with not the monolith?
So the question is that we start with monolith and move to a kind of a separate system, and doesn't that lose a lot of work that went into it? Isn't it better to not start with the monolith? Again, I think you kind of have to start with the monolith to a degree, just because you don't know what you're building yet, and you would spend all of your time trying to think about architectural decisions and kind of get caught in a paralysis there without kind of getting value out to customers, especially at a startup stage. You need to ship things. You're basically selling features before they exist. There's not necessarily a lot of time to plan ahead. In our case, we didn't think that the code base was very evolvable. We wanted to switch to more of a Python RESTful model and away from PHP MVC. So there was no real transition path from one to the other directly. So instead, we kind of implemented a facade layer above the PHP that, based on the feature, would know which system to call. So we could put some of our new data in the newer system. But they do share tables at times. So it's not an easy transition to make necessarily.
And on that note, we're going to wrap things up. Please give